As we've said, energy is a little bit odd because there's not just a single equation for it. It's this quantity that is conserved in a closed system, but it can change forms. And so there are a lot of different types of energy. We've introduced ourselves to some of those types of energy in this module. Uh, there are some types that we can directly quantify, and we've got some equations for those, and we've encountered some of them already. So let's just take a little bit of a look at what we've got so far. So work in the physics sense is a force acting on something over a distance, and work changes the energy of that object. So work equals force times distance is a type of energy. It's the energy done by a force acting on an object. Another type of energy that we're very familiar with is kinetic energy. And for kinetic energy, that's the energy that an object has due to its motion. And kinetic energy can be calculated and quantified, and it's equal to 1/2 times the mass of the object times the speed squared. So m is the mass, that's measured in kilograms, and v is the speed. It's the magnitude of the velocity. We use the letter v because of velocity. It's the magnitude of the velocity, and that's measured in meters per second. So that's another type of energy that we've encountered. We're going to not be doing lots and lots of calculations, different types of energy, but it's just to sort of illustrate that there are different types of energy and they are calculated different ways. The energy of a photon of light is equal to a constant h called Planck's constant times another constant c, which is the speed of light, divided by the wavelength of the light. And oopsie, I misspelled Planck. There's a c in there, and c is the speed of light, and lambda is the wavelength of the light that we're talking about. So those two equations, the equation for kinetic energy and the equation for the energy of light, don't look anything like each other, but they both have the same units. They're both units of joules, and I can transform energy, kinetic energy, into energy of a photon and vice versa. And the total amount of energy is conserved, but the form that that energy takes changes in that process. Another type that we're going to encounter in these slides that I'll just write down here for you is gravitational potential energy. And that's the energy that something has by virtue of it being in a gravitational field with the potential to fall. And if it falls, then it speeds up. And really what's happening there is, as we'll see in the slides, that the force of gravity is doing work on that object over the distance that it falls, and therefore it changes the energy. And we usually use the letter U for potential energy, just physicists. So we'll put a U sub G to indicate that it's gravitational potential energy. And so that's equal to mg times h, where little g is 9.8 meters per second squared. That's the acceleration due to gravity at the surface of the Earth. And it would be different if we were on a different planet or the moon, for example. So that's the acceleration due to gravity on Earth. And h is the height. And the height is just relative to whatever starting point you want to pick for how far something can fall. And again, m is the mass of the object. And so this UG equals mgh is really very much like this work definition, because mg here is the force exerted on a mass due to gravity, and then h is the distance that force does work on an object. So let's go through the slides, and you may have noticed in several of the slides there are links to switch energy videos, and this is an educational project that provides educational videos that explain different aspects of energy, and I encourage you as you go through the course to take a look at those videos because they explain some of the same things that we're talking about, but from a different point of view, with different graphics, with different types of explanation in different language than my own and different than the book. And so they may help you understand some of the concepts. So please take advantage of those resources as we go through. We talked in the last part about the units for energy and power. Basic unit for energy is the joule. Uh, the basic unit for power is 1 joule per second. That means if I take a joule times, 1 joule per second, which is a watt, which means if I take a watt times a second, I'm back to a joule. So that's what's shown here in the first yellow box is a joule is equal to 1 watt times a second, and 1 watt is 1 joule divided by a second. So there's this very basic relationship between energy, power, and time that is analogous to the relationship between distance, speed, and time. We know from our everyday lives that the distance that we travel is equal to the speed that we're traveling. That's the rate of our motion times time. And similarly, that the speed we're going is the distance that we've traveled divided by time. And you can see that that's exactly analogous to the situation with energy and power. Energy is power times time, and power is energy divided by time. So if that may help you keep straight the relationship between energy and power. Energy is like your distance traveled, it's a total quantity of something. Power is a rate, just like the speed that you might be traveling. The book and these slides here are just providing you some of the different units for energy and power and the energy conversion factors between those. So in this table, for example, we see in the center here that a calorie, and that's a calorie with a small c, is 4.184 joules. That's the energy needed to raise the temperature of 1 gram of water by 1 degree C. A food calorie is actually 1,000 calories with a little c, which can be confusing. That's technically a kilocalorie, but on food labels it's just called a calorie, but they use a capital C. So a food calorie is 1,000 times this number of joules, or 4,184. You don't need to memorize these units, but it can be handy to, as you get familiar with them, to have some of these units in mind, but you can always look them up. Just the history of the horsepower, and then you can also don't need to memorize these, but I strongly encourage you to memorize some of these prefixes, in particular milli, micro on the small side. A milli is 1/1000th of something, micro is 1/1,000,000th of something, kilo, abbreviated with K, is 1,000 somethings, mega is 1,000,000 somethings, giga is 1 billion, or 10 to the 9 somethings, and we're all familiar with those from our cell phones and things like that. So just a reminder that calories and joules are different types of units. Here's a soft drink from Australia labeled as low joule as well as low calorie. Just means low energy, not as much stored potential energy in there. These tables, and you can also look them up, have the energy content equivalent for different things, and it's the energy per unit mass. So let's take a look, for example, at coal has 29 megajoules per kilogram. And then the next column provides that in other units of energy, kilowatt hours, which is another unit of energy, per ton, which is another unit of mass. BTU is a unit that we haven't talked about, but it may crop up in some of the homework assignments, is British thermal unit. That's just another unit of energy. So you can always look up the conversions between these and go through the videos on how to do unit conversions to get from joules to BTUs or BTUs to kilowatt hours, etc. Notice that in the top part of this column, we've got coal, oil, in the top part of this table, coal, oil, gasoline, natural gas, biomass, that's things like wood, all have between about 20 and 50 megajoules per kilogram. That means they're all pretty much the same amount of joule in a lump of that stuff. If I got a pound of coal, a pound of oil, a pound of gasoline, a pound of wood, to within a factor of 2 or 3, I'm going to have the same amount of stored chemical potential energy. And that's because that chemical potential energy is energy that ultimately was created by plant life doing photosynthesis, converting radiative energy from the sun into energy stored in the chemical bonds of molecules, hydrocarbons for the most part, things like sugars, that store chemical potential energy that can be released when it's chemically reacted with oxygen, which we do in a power plant by burning it, and we do in our bodies on a molecule by molecule basis and liberate that energy. And it's not listed on here, but if we put butter down in this table, it would have about the same amount of energy per kilogram as these fossil fuels. Notice at the bottom, however, when we talk about nuclear energy, natural uranium in the nuclear potential energy, not chemical potential energy, but the nuclear potential energy in uranium that we can tap into through nuclear reactions is 580 gigajoules per kilogram. And a giga is 1,000 times bigger than a mega, and this is 500 instead of 50, so we're at 10,000 times more stored energy in a kilogram of uranium than in a kilogram of coal. And we'll come back to that later when we talk about nuclear energy in particular. So this information is just in your book, and it's not numbers that you need to memorize, but it's useful to sort of get a handle on what they're telling you. So this table is telling you all chemical fuels have about the same amount of energy, and that can even extend to food. And nuclear fuel has about 10,000 times more stored potential energy than chemical energy. So I mentioned at the beginning, we talked about energy and work. Work can change the energy of an object, and here we see the relationship that I was talking about on the notepad here, that work is force times distance, and the force due to gravity is m times g at the surface of the Earth, and the distance that gravity makes something fall is just the height that it falls, so the work done is m times g times h, and so we can then see how we get the equation for gravitational potential energy just from the physics definition of work. And here's just some examples about how much energy it takes, for example, to stand up. If you squat and you raise yourself by 17 centimeters and your weight is 600 newtons, that takes 100 joules. If you did it in 1 second, you would be using 100 watts of power, because that would be 100 joules per second. The other specific type of energy that I mentioned earlier is kinetic energy. That's the energy of motion. And there's this straightforward equation for that. The kinetic energy of something, the energy due to its motion, is just 1/2 times its mass times its speed squared. And that means that if you double your speed, you increase your kinetic energy by a factor of 4. And if you're changing your energy, it takes work to do that. Some force must be acting on you to do that. Remember that Newton's first law tells us that unless a force is acting on us, we continue at a constant velocity, even if that velocity is not 0. So without any forces acting on us, if you're cruising along at 50 miles an hour, you'll keep going 50 miles an hour until the end of time. Some force is required to change that energy and slow you down. And that force is the force of friction. And friction is a real bugaboo. It's the thing that sort of makes it so we can't have perpetual motion machines and we can't get something for nothing. We always lose a little bit of energy due to friction. And so friction is a force. It's not a force that is easily quantifiable with a simple equation unless we have it depends on the specific situation that we're dealing with. And so if we just imagine a block on the surface of a table, and I'm just playing with my iPad's drawing abilities here, and I give this block a push so that it starts sliding to the right across the table, and you can do this on your own. What will happen is that block will slide to a stop, and there's a demonstration that we've got in this module that illustrates that. Well, if it's moving along here, then that means that the block, if I give it a push, it's traveling along at some velocity, at some speed, v. And this is right after the push. And what will happen is, after friction acts on it, after friction with the table, the block will have come to a stop over here where the initial velocity was greater than 0. It comes to a stop, and that means that there must have been a force acting on it. So friction did work. The force of friction acted on this block against the direction that it was moving, and the amount of work that it did was equal to the force of friction, which I'll just call F sub friction, times the distance that the thing traveled. So if our block was initially here, it traveled this far, which I'll call d, so that the work done by friction is equal to F friction times d. Well, what's the force of friction? We have to know things that we're not going to worry about in this class, like coefficients of friction, how heavy the block is, what the materials are made of. We don't really care about that. But this is our usual work equation. It's a force times a distance. And so that changed the energy. So the kinetic energy of that block went to 0, but it started at some non-zero number up here after I pushed it. So where did that energy go? The change in the kinetic energy must have, the decrease in the kinetic energy must have been compensated for by an increase in another kind of energy, and the energy was converted to thermal energy. And thermal energy is going to be the topic of the next chapter, and literally thermal energy is actually still kinetic energy, but it's the kinetic energy of the atoms and molecules in a substance. And so while the block as a whole stopped, the surface of the block and the surface of the table got a little bit warmer as the molecules that make up the wood of that block and the table that it was on started vibrating a little bit due to that frictional force. So the total energy of the system was conserved, but from a practical standpoint, it's kind of lost. We don't really have useful energy. We had the block moving, friction came along, it changed the kinetic energy of that block from useful motion of something moving to useful energy of something moving to a slight increase in the temperature of things, which maybe if we wanted to warm our hands up, friction can be handy that way, but it's not something that we can use to generate electricity, for example.